Hello, and welcome to the 5th tutorial of the series, where hopefully it's going to be one of the last ones that we do. So we're entering the finale, I guess, of this tutorial series. Before we begin, you should open up the file that we've done the last time during tutorial number 4, I believe. Yes, tutorial number 4. If you don't have the file, you can just simply download it from the description here. And once you open up the Rhino file and the Grasshopper file, you should see something like this, right? So I won't go into detail of what we did last time. If you followed through, you know. But the basics of it is that here we have two copies of the same code, right? A cluster version and a exploded, like a regular definition version. So I will not be using the definition version. I can get rid of that. I will be using the cluster version though. And this one just gives me all of the, let's just see if it works though. Yeah, this one just gives me all of the possible permutations of any tile here. Okay, so that's that. Before we can use this, we need to set up the world, so to say, the initial conditions for this to work. And let me actually break it down for you, right? So we have these points here that are going to be wrapped with these elements, right? So it's going to be a voxelized 3D grid. Actually, maybe this would be a bit more easier to understand. So let me just unlock the layer of those points, select all of them. I'll just create a point container up like that and set multiple points. Okay, so now I have them in my in Grasshopper. Let me just log this again so that I don't accidentally select them or move them around. So I have these points, and by the way, these points are created through the through the Game of Life algorithm that you can also see how it's done in, where is it? 4.3 and 4.2 in these two tutorials right here, right? So if you need to create this kind of set of points, then you can use that algorithm to do so. What's nice about them is that they're I wouldn't say voxelized, but basically they conform to a three-dimensional grid that's 10 by 10 units, and all of our voxels are 10 by 10 units big, right? So it's kind of a match between these. Right. So now let's create a voxelized Martian cube structure. So to do that, I will first just show you what I'm after. So as long as you have Cocoon plugin installed, and you can download it from just Google it. As long as you have Cocoon plugin installed, you can quickly wrap the default like Marching Cubes mesh around this point grid by just choosing a point charge here, connecting the points to the point charge input. For the radius, that's the gap between the points, I will use 10. For the strength, I never know. Since it's all going to be uniformal, I'll just use strength 1 for every single point. So the radius is the important one, right? So now we have a bunch of point charges. And then I can use the Cocoon node of Cocoon plugin and just connect my charges to the charge input here. The target ISO value, I'll get back to that, but it's basically a value between 0 and 1. So I can use 0.5 with additional resolution like that. And then we'll kind of play around with the slider. Then for cell size, cell size is basically how big our voxels are, and we know for sure that they are 10 units big. So I just connect my radius to the cell size as well, right? So 10. And execute is, I just have a toggle for it. I'll turn it on and forget about it, right? So once we turn it on, behind that, once we turn it on, this kind of a shape appears. Not the prettiest one because it's very low resolution, but you can easily add resolution by just subdividing with Catmull-Clark subdivision or something like that. And then you end up with a few blobs here and there. But for now, we want the low-res version because this guy right here, it has like it's made out of these segments, right? Only that it's of course all internalized and much faster than what we are going to have. But at the same time, there's no way on how to change what kind of library of polygons it uses, because first of all, it's calculated in a slightly different way. Second of all, it's it's Marching Cubes algorithm. That's what it does. It just uses the lowest possible polygon count elements that it can. If I change the ISO value though, you can see the higher the ISO value, the smaller the gaps become, right? The larger the ISO value, the thicker this boy gets. The thing is, if we have ISO of 0 or 1, it's gonna break. And what we have here, like in all of these, is as if we were using ISO value of 0.5, because every single corner point of every single voxel element touches the edge of the voxel right at the midpoint, meaning that's ISO value of 0.5. To break it down even more, just so that it's very clear, basically to use this Marching Cubes algorithm, first Cocoon creates this kind of voxelized space, right? And by voxelized space, I mean, let's go here, just create a quick box. That's our single voxel, move it here. And let's just do 1, 2, like that. Copy to the other side, like that. And let's copy it upwards. Right? So that's kind of what I mean by voxelized space, actually. Silhouette, lock, delete. Right? So everything is divided up into these small cubes. And inside of that voxelized structure, or not structure, but world space, voxelized space, we have a few points that are touching perfectly the corners of our voxels. So let's say here and here, right? And then what this Marching Cubes algorithm does, it takes voxel 1, right? Like that. And it checks which corners of the voxel have a point on it, right? So let me copy this to the side. So in this case, this one has a point right here. And then it will check in the library which one of the permutations of all of these voxels conform to that. So I can tell that since it's a single point and only type 1 uses a single point, it's going to use that, and the permutation of it is going to be like a mirrored version of this guy right here. So for instance, if I were to just quickly copy this one here, and I'll just be a bit messy about it. Yeah, let's be messy about it. Like that. And is it like that? Yeah, it's gonna be like that. Here to midpoint. It's gonna be something like this, right? So it reacts to that point here and creates a voxel for us, a voxel element for us. So once it finds the correct permutation, it just moves it in place, right? Like that. And then checks the second voxel, and this one will have 2 points, right? I'm talking about Kind of messy. There we go. I'm talking about this voxel right here with these 2 points. So it's going to use those 2. So that's type 2, right? Well, a version of type 2. So I'll just take type 2 and I'll move it in place. Something like that, right? And then it will go around all of the voxels. So it's going to march, right, through the voxel list, and it's going to choose what kind of permutations of what kind of type it needs. So it's, you're gonna end up with something like that. There we go. This kind of guy right here. That's 2 points wrapped around. So in this case, let me turn this back on. In this case, you can see it here, right? 2 points, same shape, right? So that's cool, but we want it to be automated, and also we want it to be not automated, sorry, we want it to be custom, right? We want to have the possibility to change the elements. So I'll need to rebuild the whole idea of it. Actually, let me leave this. I'll need to rebuild the whole idea of it in Grasshopper, the principles of it. So I'll just keep this here. I'll create a new point container, point here, and just unlock these cellular automata points, grab them, set multiple points. Okay, so I have them here again. Yeah, I could have just copied that one. Well, doesn't matter. Let me hide this for now. There we go. We have a bunch of points. So the first thing is to create a space, a voxelized space around them, right? So to do that, the first thing that I'm going to do is I'm going to create a bounding box around all of my points. Bounding box, like that. And by default, the bounding box will not do anything. That's because it's set to be per object, right? So we want to make this into union box. If you right click on it, select union box, then it's going to create a bounding box around all of the points rather than every single point individually. The plane of the bounding box is fine. World XY, everything is aligned with XY coordinates here. And I'll talk about where this point cloud needs to be placed later, but you can see that it aligns with Y and X axes perfectly. And you would think that, well, now we start subdividing it, right? But the problem is that it's not enough to just have a bounding box. We also need the bounding box to be thicker by 1 voxel to each side, right? Because the voxels that we're going to have, for instance, for this point right in the corner, right? The voxels that we're going to have need to surround this point. And right now it's just one. It's going to be a single voxel that's kind of touching that point. And it basically needs to be done for every single point around the perimeter, well, around the outer boundary of this box. So we need to kind of make it bigger by 10 units because that's the size of our voxel. We need to make it bigger in all the directions. Of course, many ways to do that. The one that I choose is I'll deconstruct the box. Deconstruct box, which will give me X dimension, Y dimension, and Z dimension, right? And I will create I will deconstruct the domains of the box as well. These are domains, by the way. The dimensions are not in units, but rather in it's a domain. So the box starts at 0 in X direction and ends at 40, right? So if the box was moved slightly to the left or to the right, then this would be like a minus 10 to 30 or something like that. It just helps us understand positioning in accordance to the plane that we're using. In this case, we don't care. We just deconstruct not plane, domain. Deconstruct domain, right? And I'll just simply, actually, just to make it clear, I'll use merge and connect these three into the merge component, like so, just to have everything, like all three of these in the same list, right? And I'll use deconstruct domain on this. So the output that I get is two lists, one being 0, 0, 0, 0, and the other one being the max of the domain, 40, 40, 30, right? So I know that it's 40 by 40 by 30. So 40 to the left, 40 to the 14 x, 14 y, 13 z, right? And it all starts at 0, 0, 0 locus, which is really nice for us. So now I need to, for all of my starts, I need to subtract one voxel size, right? Because I'll be constructing the box from this. So I need to subtract one voxel size. And let me just type in 10. That's my voxel size. And let me create a number container. So just empty number container. Right click on that and I'll just call it voxel size. Just so that disconnecting and reconnecting stuff to this is going to be easier. So again, for starts, I need to subtract from this list the voxel size, like so, right? And let me place it here. So now it's going to be -10, of course, for like every, so it starts in -10 in all places, in all directions. And now for the ends, I need to add, so addition, I need to add the voxel size, like that. So it ends at like 50, 50, 40. All right, that is done. And now, instead of subdividing this thing, let's create a single voxel first, right? So right now I know where it needs to start at -10, -10, -10, and I know where it needs to kind of end, right? So I don't really care about that, and I'll explain it in a bit. This is going to be used for something else. But first of all, let's create a single voxel box, right? So I'll just disable my union box. And I want that voxel box to start at -10, -10, -10. So like a box right here going down. So that's going to be, what are we going to use? Box domain box, like that. And that box is going to be aligned with XY plane, of course, like that. And the size of that box are going to be the voxel size, right? So 10 by 10 by 10. Okay, that's cool. It's created, but the problem is that it's not, like, the location from where it starts is not correct. It starts from 0, 0, 0. And again, I need it to start at -10, -10, -10. So the origin of XY plane needs to be -10, -10, -10, of course. So I have a voxel size here. If I just grab a negative, that's just going to, that's just going to give me -10 here. And if I construct a point and feed it into X, Y, Z, you can see my point is here. So that's its coordinates, and I can use this as my origin. So now my first voxel is placed properly. Okay. Moving on, I will need to array this box, right? Just to have something like this. So I'll array this box in X, Y, and Z directions. So array box, or box array, let's use that. The center oh, sorry, the cell for array is the same box. That's convenient. And X, Y, Z. So if I were to say 10 by 10 by 10, 10 by 10 by 10, this is way too big. It would work though, of course, but this is way too big, and we always want to have the smallest amount of voxels possible, right? But at least this works. So instead of having the slider, I need to have 3 values. And good thing that I have 3 values here, right? So just in case if this box is moved to the side, I want to subtract from the maximum dimension. I want to subtract the minimum, like that. And in this case, it is going to be slightly in the negatives because we subtracted the voxel size, right? So right now I have the size of how big my bounding box should be. Precisely, like 60, 60, 50. That is great because then we can tell how many voxels we're gonna need in X, Y, and Z direction by just simply dividing the length of the desired box by the voxel size, like that, right? So now we have, okay, we'll need 6, 6, and 5 voxels, right? And 6 in X, 6 in Y, and 5 in Z. So this gives us a list. This requires us to give it 3 separate numbers, so we need to separate it. I'll just use list item. List item, connect it like so. Always gives us the first item on the list. If we zoom in and click on the plus sign in the base here, that's the first item, that's the second, and that's the third. And I just connect X to X, Y to Y, Z to Z. There we go. So now, in doing so, it's a bit weird, but in doing so, doesn't matter how many points we have and how much they're spread apart. It's going to always create the smallest amount of voxels needed to wrap around this geometry. Kinda. It will create empty voxels as well. You could optimize for that, but honestly, this is good enough. So we have something like this. Let me group all of this like that. Just to have it clean. What I want now is, let's extract a single voxel. List item. So that gives me the first one. And if I, how many do I get? 180. So 0.179. So if I go through this list, you can see, I'm checking every voxel. That's nice. I will need to do that. And let's just grab wires, brep wireframe. Nope, wrong one. Wires, brep wireframe. Just connect it like so and hide the box itself, just so that it's cleaner, it's nicer to look at. And now let's find 3, oh, even 2. Okay, for instance, this voxel right here will require us to use element type 1, right? So this is where this cluster comes back, like that. Let's see. Which one am I using here? Element type 8. Okay, so I'll replace all of this with element type 1. So cage curve. Let me just select it. Set multiple curves. Perfect. Guiding points. Set multiple points. Well, it's just a single one. In this case, element geometry, set multiple, well, also a single one. Okay, let's enable the preview of this. So we have 8 permutations of this, right? Okay. Actually, maybe I should have this shown like that. Like that. Okay, so this guy right here, we know for certain that this guy right here is going to use top, right, back. What the heck? Oh, let's see if that's gonna work. It seems like our permutations are messing up a little bit. Or maybe it's just the orientation value. We'll see. We'll see. So for now, that is very strange. For now, let's just check out if this is gonna work or not. So here I have rules for our permutations. If it doesn't work, we'll troubleshoot it. Remember where we did the for every corner that was being checked, we did false or true statements. So those were the rules. We need to ask for this particular voxel, well, for every particular voxel, we need to ask the same question. Does it have a point on its corner? And if it does, on which corners does it have the point in? And we need to construct not the rules, but like true or false statements for every corner. So the first thing that we do is we extract the corners of this box, right? Box corners, like that. And then we connect these box corners back into a single list with merge. I mean, with evaluate box you could do it in a much cleaner way, but honestly it's just a little bit of connecting so that it's not a big deal. Like that. And we get our corners here, right here. So these are just simply points, which is not that that great for us. We need to have true or false statements, right? So and for that we need to, let me hide this. For that we need to have this single corner here set to be true. The first thing that I'm going to do is I'll grab point list here. Let's give it a bigger number for the size, like that. Oh, that's very big. So for that, and so I know that in my list, 0.6 here will need to have true, while everything else gets false. Let's just actually see if here we do have 0.6 saying true in any one of these lists. Oh crap. Okay, I'll need to revisit this again. I messed up. So tile variation, let's see, where does it mess up? I assume it's going to be create set, find similar. Okay, let's see this one first. Of course, once I figure this out, I will send the updated version of it. And just to save some time, let me pause the video for a bit. Alright, so there was a problem, a mistake that I made during the last tutorial, which I will solve now, and the cluster, the correct cluster, is going to be available to download from the description of this video. But the problem was that here I was messing too much with, inside of the cluster, I was messing too much with grafting and data trees. And some of the data trees got shuffled and stopped being correct. So in this case, you can see here, the mirror comes into D2, while rotate comes into D1, while here the transform from mirror comes into D1, while the rotate repetitions come into D2. So let's just see if we simply change it up. So mirror comes into D1 and rotate comes into D2 here. If that simple trick will work, so I just changed the inputs here. Save and close. Enable preview. Okay, that corner is there, there. These two are the same, meaning it doesn't work. Okay, we come back here, and instead of constantly trying to change it and revisiting it, I will just here enable the preview of my tile output, like so. And where's my frame? It's gonna be here. Okay, so that didn't solve it. Probably there are some more issues with it. So instead what I'm going to do is I'll get rid of the data structure right here, and also right here, right? So these are going to be two places where I get rid of the data structure and everything is forced onto a single list. Wait. I mean, here. So many merges. Right, so these two. Let's start off by flattening. So I'll need to flatten many things. Not many, 4. So that's not a lot. So here let's start working with the geometry. Where I have mirror geometry, like the output of it, I will flatten this guy. So instead of using the regular flatten, right clicking and choosing flatten, I'll use the flatten node just so that it's clearer, I guess, at the expense of how many nodes we have on the screen. So that's flattened, and also I need to flatten the second input here, like that. That is also flattened. And here I'm kind of recreating the data tree, which I don't need to do, so I'll get rid of the graph. Okay, so everything that comes into the last merge gets flattened, and I don't recreate any kind of a data tree after the merge. Still, mirror, flattened version of the mirror geometry output comes into first input, and then all of my rotations from before come into my second input. Cool. Next up, so that one is fixed. Where am I? So that one is fixed. Next up here, if I'm getting rid of the data tree structure, I don't really need this guy anymore, right? So I'll just delete it. I'll use flatten again for my comp between my which transform is this? Between my mirror transform and my rotation, repetitions here. So I'll flatten that one out, connect it like so, and again flatten. This is gonna be the last one. my rotation transformations are going to get flattened as well. They're going into D2. So that should fix it. And let's just ungraft this. Okay. Checking time. So that is here, that is here, that's there, that's there, there. Yep. No duplicates. Everything seems to be working quite well. So that's great. Hopefully this solved it. If we'll see any problems later on, I'll revisit this and I guess fix it again. But for now it's just the 4 flattens that we needed to use, and also the wires needed to correspond to what comes in first into the merge and what comes in second. Once I've done that, I click on this opened box here and click on save and close, and now my tile is updated. Oh yeah, we need to double check. We were checking for wait, which one? Where is it? There we go. 6, right? So in my rules, there needs to be a rule around 0.6 somewhere here. Please work. Please work. Oh, thank God. Okay. So here it's in my branch 6, the rule for 6 is true. Great. Meaning that now we need to create a check, so to say. So this voxel right here, it doesn't matter which one, but any voxel. In this case, it's gonna be this one. This voxel right here will check whether or not it has whether or not the point or any point in this point cloud is touching a corner of the voxel, right? So the checking procedure is exactly the same as what we've done with the cluster here, if you remember it from the last tutorial. And it's going to be checking for closest points, CP, closest point component, and checking whether or not any one of these points are closer than 0.001 or whatever to any one of these points. And if they are, they should turn true, right? So I want to check each one of these points, the corner points of my voxel, separately, meaning I need to graft the input here. So now every single point on my box corners will be checked separately. And the point cloud to search in is gonna be my points right from the start. So I just connect them with this long wire right here. There we go. Okay. And now if I grab a panel and I check with the panel, I can see at my point 0 corner point, the closest point that I can get is 17 centimeters away, and this one is 14, blah 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 blah, and 0.6, this corner point here hits a 0, right? Meaning that there is indeed a point on top of it in that particular point cloud that we're using. So I need this to be true or false statements rather than numbers. So I can ask, is it, we could ask for equality, is it equal to 0? Yes or no? But that might suck with tolerances. So instead, I'm gonna use smaller than. Is the number here, the distance, smaller than 0.01? Something like this. And then I get my answers. No, 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 yes. That is super. So I have that working out for me. how should we? Okay, we'll need to do additional check, but I'll come back to that later. Just to kind of talk about it just for a second. What happens when every other corner point on the box has a point on it except except corner point 6, right? Because we don't have in these variations we don't have more than 4 points in each voxel. So what happens then? But we'll come back to that rule in a second. For now, I'm just gonna leave it as it is, right? So I have my answers here, smaller or equal to 0.01, and I'll just flatten them up into a single list, right? So I have a list here, and I have rules here, which means that I can kind of ask whether or not these fit, right? So what I'm going to be doing is I'll just simply be going to ask for equality. Is this rule equality? Are these rules equal to these rules, right? And what I'm gonna get is, what the heck is going on? Yeah, for 6, so it's basically checking whether or not the first item on every list, if here it's false, is it false here? If here it's true, is it true here, right? So it's how many hits for similarity does it find for every single item in the list. Why is this all true? Oh, good, it's false. That's good. So it only should say that, yeah, that particular permutation belongs to this particular voxel only if all of these are true, right? So I can use mass addition for this, and I can ask whether or not this mass addition, because it will add up all of the falses as zeros and all of the trues as ones, right? So I can ask whether or not this mass addition is equal to 8, because that's how many corner points we have. If all of the corner points match up, that means that particular permutation belongs to this particular voxel, right? Okay, we have that going on. So the answer is gonna be no. Yep. So value 6 is gonna be true. Nice. So that means, oh yeah, and also that true statement we need to use to get the correct permutation out of here, right? Out of here. So I know that it's going to be also coincidentally in tree branch 6, data tree branch 6. So we need to extract just that. I can do that with a component that's called pick and choose. Pick and choose, which asks me for a pattern. I'll just give it a pattern like so. And all of the falses will use index 0 here, input stream 0. And all of the trues will use input stream 1, which means I can simply connect this to input stream 1, and every time when it gets a true, it's going to give us an output like that. And you can see here it's orange. That is okay. It's just because it gives us nulls here, right? Because it doesn't choose all of them. There is a way on how to clean it up, but we don't want to have too many nodes here, so I'll just leave this orange, let it complain for a bit. Then we need to clean this all up. Even if I flatten this output, it's still, you know, a bunch of nulls, which I don't need. So I'll clean tree. And here I just need to specify that nulls, remove nulls, needs to be turned to true, which is the case. So I'll just connect it to the tree input. And now if I check clean, group with two objects. And remember, those two objects are the locus point here, which is from where we're going to move, and the object itself, right? The triangle in this case. All right. So now it's time to see if this is gonna work or not. Right, I want to move it to this position, right? So I will well, first of all, that's a group, right? So I want to ungroup it. Ungroup. Okay. And then it's when I ungroup it, I'll always have the first item on the list being the locus point, while the second, third, and so on, doesn't matter how many, is going to be my surfaces. So I'll split the list at index 1. I would want to say 1. Yes, good. Okay, so split list at index 1. And it gives me the locus point here from where I move and the trimmed surface here. That's perfect. Okay, so moving on, now it's just creating a vector between, let me just make a point container here, just so that it's easier to understand what I'm after. So create a vector between this point right here and the 0 point here, and it's always going to be a 0 point in this voxel, which is very convenient for us because we can just simply grab a 0 point from here, or just use list item. It's maybe gonna be cleaner a bit like that. See, list item gives us first item on the list, which is this point here. So if I just for clarity purposes, if I were to draw a line between between this point here and this point here, you can see it's basically going to say, oh, I need this one, and move it along this line, right? So instead of a line, of course, I create a vector between 2 points, between where I move, between from where I move to the point to which I move here. So I get a vector, and then all I need to do is use move. Geometry that I move is my the surface here, like that, trimmed surface, and vector is here. Yay, that works. Let me hide a few things here and there. That's fine, we don't need to see that. Okay, so that works nicely, and as you can see, all these two are not necessary. These are just for clarity purposes. We preview these. Right, so now we have this going on. Let's change index to 3. Yes. once we shuffle, not shuffle, but once we go through this list, see, this one is empty, so it doesn't receive an element. This one is also empty. This one receives a triangle here at corner point 6. This one gets one here. This one gets one here. Nope, wait, this one is empty. What am I talking? And so on. So sometimes, once it hits precisely that tile variation, it's going to give you a corresponding voxel element. Neat. Okay, that is done and that works. Let's group some things up just to make it cleaner, and then we will do a very boring thing. But first, let's group it up. So I'll delete this or not. I'll just select all of this like that. Make a group until I clean it up. Right? And now I need to do this for every single type of a voxel that I have. So I have 1, 2, 3, 4, 9, 13. I have 13 types, right, of voxels. Wait, is it 13? It's 14. It's not 13. I have 14 types of voxels. So what I'll need to do is select select this whole thing, because I will need to check for equality and you know, check which one of these tiles will work. So I select this whole group, copy, paste. So that's 2, and then we do the fun bit. Okay, that is done. Really fun stuff. Let me just double check if that actually, if I didn't mess it up. All of that seems fine. Okay, seems to be okay. So, and of course you can look at all of the permutations of all of these now. But let's not do that because it's too much in your face, so to say. And this guy right here is basically just what we're moving. So why do we see it? Is it here? Yes, it's because it's here. Let's pick and choose. Hide all of that. Okay. So here we have the cleaned group, and this one just gives us that, right? If I were to, let's find the, yeah, there we go. 1, 2, 3. 3 elements here. It's probably going to be L shape, this one. Type 4. Element type 4. In this case, element type 4, after cleaning up, gives us, please work, yes, 2 groups. So this indicates that our optimization is not perfect, meaning it's not optimizing all of the variations, but this is honestly good enough. The improvement of speed would just be minimal if we were to optimize it further. So that's good enough. Meaning that right now this part here needs to somehow choose which one element it will use, right? And of course this one is empty now. To do that, all we need to do is just merge. So we simply merge, come on, merge that and that and that and that. Oh, don't do that. That's not good to do. So every time when you want to save time by not doing the data trees, Grasshopper just punishes you with all of the wires that you need to connect. So Grasshopper is a tough mistress, hard to please. It will just punish you if you don't accept its data trees. But we're also tough, so we don't care. We'll just connect all of the wires like it's no big deal. And here, so remember where I said that we're not optimizing it correctly? I don't need that. Where we don't optimize it correctly. The output of this one is of course going to be 2 groups, right? So it has like 2 variations which kind of fit here, and it's just basically going to be a duplicate. So we need to get rid of that. To get rid of that, we will just use list item. Just grab the first variation, connect it here. Ta-da! So now it works. Okay, that's cool. And you can see, oh yeah, it picks these 2 for some, I don't know. It's late, I wanna go to sleep. So this all works, and you can see even the wire changes. Oh, actually it's gonna be pretty cool if we just grab that slider. So with this one we're kind of manually marching through every voxel that we have. If I grab that slider like this and I kind of move it around, you can see, you know, this is which types it picks up. And sometimes, wait, it's just all orange. That means voxel is empty. So that works. Nice. We're getting there. We're very close. So now, since that one works, we need to automate it, right? We need to kind of, well, we don't want to just do this, bake it out, then do this, bake it out, do this, bake it out. We want it to be automated, right? So for that, we need to construct a loop. Very easy to do in coding, and for doing that in base Grasshopper, we will be using anemone. What am I writing? Anemone has two nodes, which first one is start, loop start. Second one is end, loop end. There we go. These two nodes connect like that, and they basically loop information, right? So this is how the first input for the loop start is how many times should it repeat the loop, right? So once it finishes doing this, right, it jumps to here. That's the second loop. That's the third, fourth, and so on. So how many times does it need to do that? Well, it needs to do it for how many voxels we have, right? List length. We just measure the list length of our array box, like so. And the answer is going to be 180. We connect it. The thing is that after 180 iterations, iteration 0 for the loop is this guy right here. So it's kind of eating up the first step, right? It's eating up. So actually, instead of 180, we need 179, like -1 always. So here I'll just right click on the output of the list length, click on expression and type in x -1. Commit changes, 179. Okay. Next one is trigger for repeat or restart. So that's a button. Every time we want to restart this this loop, we will hit the button, right? Third one is, what's the data that we want to loop? Well, actually, there's no data that comes in from here that we want to loop around. We just want this guy to keep looping. I keep using the word loop, but yeah, I mean, I guess that makes sense. So this guy needs to keep looping, and we need to always ask which step are you at, which step are you at, which step are, and it's going to count it for us. And the counter is this thing right here, right? So if let's say if I have a number 1 plus, not plus, but how do we do that? Merge. Let's say I have a number 1 and I merge it with this. This is an empty list that comes in, it merges with the number 1. So right now in that particular list I have null and the 1, right? And if I were to connect it to the input of the loop end, it will just loop around 179 times, meaning by the end we'll have, oh, it's still doing it. Let's wait. I don't know what's up with anemone, but it's pretty slow. So by the end we'll have 180 items, well, 181 because the first one is null, items in the list, and all of them are going to be 1. So it keeps adding this guy right to the list 180 times. The cool part is the counter, that if I now connect the panel to the counter. If I click the restart button, you can see it keeps counting. That is very, very convenient for us because we will not need to move that slider which I lost. I deleted it. Nice going. Okay, so here where we chose which voxel we're gonna use, we won't need it. We won't need to use a slider. Instead, we'll just use a counter, right? Okay, and right now the counter is at the end of the whole loop, so it's the last voxel. All right, almost there. So we have that going on. Now we have loop end here. Like, come on. I usually just move the loop end to where my definition ends, and I'll keep the merge, but I'll just delete the number 1, because instead of that number, what we want to keep adding is these voxel elements right here, right? So as it loops around, it keeps adding them, keeps adding the output of this one to the list, right? So it's basically like as if we were recording data. Immediately as I plug it in, I can tell that there's gonna be a problem, and that problem is going to be this dashed line here. It means it kind of creates a screwed up, almost said a bad word, it will create a screwed up, what the, why is that 180? Oh, that's because it remembers the ones. Okay, we don't care. It creates a screwed up data tree. I will just flatten this, and now it's not screwed up anymore, and once we reset it, the ones will be gone, and it's just going to keep saving the element here. So, moment of truth. Look. There we go. That's nice. Oh, broke there. Broke in other places. Keeps breaking. Kinda works, but not really. Works for these. That's nice. Okay. Very close. Let's bake this out. Should be nice. So to bake it out, the merge is where everything is kept, right? So I'll just use brep here, like that, and I'll just kind of group this, hide that, hide everything. Actually, hide everything except the brep. Bake that one out. Default is fine. Oh, actually, bake and group. Okay, move that to the side. Minimize that and zoom in. Let's see. That is good. Good, good, good. That is not good. Yeah. Some of these are really messed up, but others are fine. Okay, so one more thing that we need to fix is basically how does it treat when it has more than 4 points on all of the corners of the voxel. You can see here that it's, you know, the maximum points that you have here is 4. So how does it treat 5, 6, or 7, or even 8 points here? The answer to that is it inverts the logic, right? So if it's the same thing, let me just grab this real quick. This element right here is going to be created also, not just by this, but also if you have this, and this. Right? So that means that an inverted version of this element also inverted version of the rules for this element will also create this particular permutation, right? So coming back here, where we have our smaller than value, right? There needs to be an additional, oh no, will I need to reconnect all of this? Can we? Oh boy. There needs to be some sort of a, is there like a control? No, shift, no, alt, no, control shift. Ooh, that's okay, control shift. So I'll just create boolean, empty boolean component, hold control shift. Why doesn't it work now? Oh, there we go. And connect it to the boolean component instead, like so. Whew. That was scary. I thought I'll need to reconnect this. Anyway, we have our rules here for some particular voxel. Let's see which one it is. That guy right there. Right, and in this case the rules are going to be fine for it. It's just going to create a triangle. But if it had all points here, it should be able to, all points except that single corner point, it should be able to create a voxel as well. So I will ask, is this number, wait, which one? The distance is smaller than okay, so let's see it like that. Here we have an answer, right? If we do mass addition for this guy, we will know that how many true statements we have. 1, right? So that means it's only one corner. But we will ask, is this larger than 4? I want to say 4. Either larger than 4 or larger or equal to 5. So let's do 5. Is it larger or equal to 5? So we get an answer no, which means it should use this answer here, right? Since it's no. If it were true, that means this answer right here would need to be flipped, right? So everything that was false would become true and everything that's true would become false. A flipped version would be just using not gate, like that, connecting it like so, right? Something like this, and now it's flipped. And basically to choose whether or not we're using the original or the not version. How do I arrange this? Original or the not version, all we need to do is just choose filter. Filter, stream filter. The gate for it is the true or false statement. And we have 2 inputs. So if it's false, that means it should use the original, right? Rules. But if it's true, if there are more than or equal to 5 true statements in here, then it should use the inverted version, like so. Now connected here. Okay, it doesn't seem like it broke anything. That is really nice. And let's run this again and pray that it's gonna work. Things seem to be closing up. There is a problem, or is it a problem? Let's see. Are you problematic? You seem to be problematic. But all of that seems to be working okay now. Oh, that's not No, that's fine. That's actually how it should be, right? Right? No. That's an opening. Okay. We'll need to troubleshoot that part. Why does it make an opening there? Okay. Thanks to some movie magic, I have figured it out, and you didn't need to look at my screen as I was trying different things. So it was this voxel right here that was problematic, right? And basically it registers these 2 points and also these 2 points. Let me turn those on actually. Yeah, there we go. So we have this type of element right here, and if I check the library, it's type 13 with 4 points, which is kind of flipped in a sense that this should be registered as a it should be registering as if these 2 points were empty, or these 4 points were empty, while all other ones were full, which got me thinking that probably everywhere where we have 4 points, right, so right in the middle of the amount of points that we can have, so everywhere where we have 4 points, that where is it, that filtering of with the not statement might screw us over, and it's like a Schrodinger's cat, right? It can be either this or this, right? So in reality, we could have additional checks for cornering, not cornering, but surrounding voxels and what kind of polygons are used there, and according to that extract the rule set, or we could just say screw it and then rotate the parts which are problematic the way that we want and keep going with our definition, which doesn't, you know, in this case it's going to work. And if I actually, let me do it this way, cocoon, let's go for custom preview like that. Come on, custom preview like that, swatch white but with transparency, something like this, and also custom preview here. This is just for me to check whether or not it works, right? And this one is going to be blue. Oh, darker, like that. So you can see that everything overlays correctly, right? So let's redo this, run it again. Okay, so this part seems to be filling everything up nicely, like that. There we go. Okay, so that works, and at least now you know why it's called marching cubes algorithm, right? So that works, meaning I don't need to see that part anymore. All of this should join into a closed BREP. Let's see, well, into 3 closed BREPs. Let's just see if that's the case. Yes, it is. That is perfect. Okay, so for this tutorial we're done. We have our shape, and just to show you the potential of it, for instance here, if I were to say, oh, this is gonna be so stupid, No, let's do it this way. Duplicate border, offset. I have no idea. That's 3 centimeters. Let's offset by 1 centimeter. Extrude curve. Whoop. Something stupid like that. And I'll just select these two. And I'll jump back into element type 1, element geometry, set multiple geometries like that. And now let's hit that reset button. Cool, huh? Which means we can do many really cool things with it, which I'm quite excited about. Looks so stupid. Anyway, next up I will create a title screen for this particular tutorial, and I'll of course speed it up. I'll make a time lapse of it because it's definitely not a part of tutorial. So we're done with this one for now. Next up, we will have statistics. So we'll extract statistics out of the structures that we have here, just so that we can know for certain how many different types of elements we'll need to, print out, laser cut, or CNC mill out to produce an object like this. So we'll have like statistics for this kind of structure. That's going to be the next tutorial aimed at production, and the last tutorial is going to be V-Ray rendering, right? So I'll show you how to render out a little bit more cartoonish style renders with V-Ray for Rhino. Said that, just to be clear, V-Ray for Rhino is a very, let's call it handicapped version of the V-Ray for 3ds Max, the original one, because V-Ray for Rhino doesn't let you play around with light information. So which means that you cannot have true cell shaded objects. So cartoony stuff becomes quite tricky to do, but we'll try either way. But that's going to be probably sometime next week. For now, we're done with the tutorial, and I'll move on doing the whatchamacallit, the time lapse for the intro.